Here's another demo, this time driving a 16-bit expander chip with SPI. It's an MCP23S17, which has 16 general purpose I/O pins, which can be individually configured as inputs or outputs. The surface mount versions can be a lot cheaper than the larger through-hole ones. I just found 10 of these for £10 UK, including postage. Just make sure you get the 23S17 version for SPI as opposed to the 23017. Now, these carrier boards are quite handy for surface mount lash-ups, although you'll need a fine tip soldering iron and a steady hand. Now, it's quite a complex beast with several modes of operation, so I'm just going to scratch the surface and turn some LEDs on and off. I've not studied it thoroughly, so apologies if I state something which is incorrect. Here are the pin mappings. The 16 I/O pins are split into two 8-bit ports, A and B, and I'm using the 3 least significant bits of port A to control 3 LEDs. Now, don't forget to add a current limiting resistor to each one. I'm using some of my breadboard test modules with an LED and 2K2 resistor on a 2-pin header plug. I'll use 4th again, just as a convenient way to assign names to numbers and to define simple routines. There's no attempt to make the code efficient, as the prime objective is clarity. And hopefully you can see what's going on even if you're not familiar with 4th. Here's the allocation of aux out signals. The clock and data out, or MOSI, are fixed, and I'm using aux 1 and 2 for reset and chip select. These are some shorter name definitions for the built-in SPI functions to make them easier to enter on the small teletype screen. There's some utility routines, the usual chip select and deselect. Now, this chip contains several control registers accessed via a register address, and the data sheet shows hex numbers for these. Now, with previous 4th examples, I've pre-converted hex numbers to decimal to keep things simple, but this time I'll get 4th to convert them automatically, so the code matches the data sheet more obviously. Now, don't worry if this doesn't make sense. Basically, when hex is called, it makes the interpreter treat all numbers from then on as hexadecimal, and also allows you to use the conventional hex prefix 0x to avoid any ambiguity. And when dec is called, the interpreter reverts to normal behavior and treats all numbers as decimal. So here are the register addresses I need for the demo, and by invoking hex first, all numbers will be treated as hex. The I/O configuration register, IO_CON, is just shown for interest. I realised later that I don't actually need to use it. Next up is a potentially confusing area, the control byte value. And this needs sending at the start of all operations, as it identifies which chip you are talking to, even if there's only one. The value contains the chip's 3-bit address and 1 bit to indicate if it's a read or write operation. The chip's address is set by tying its 3 address pins, high or low, giving 8 possible values. The advantage is you only need 1 chip select signal if multiple chips are sharing the clock and data signals. But the downside is the address has to be sent for each operation, even if there's only 1 chip. Now, if your device doesn't have an address feature like this, or you choose not to use it, multiple devices would need a separate chip select signal for each one. The configuration register, IO_CON, contains a bit called hardware address enable, so you can choose to ignore the address pin value and force the address to always be 0. Whatever this setting is though, you still need to send the control byte value for each operation, and the 3 pins must still be tied either high or low and not left floating. Now, I've tied them to ground, so the address will be 0 regardless of the address enable setting. So all of this is captured in these 2 control byte values, which assume an address of 0. There's a value for write operations and one for read operations. I've finished with hex now, so I'll switch back to normal decimal numbers. And the registers needed for this demo just need a single data byte. So this write register routine takes two parameters, the register address and data value from the stack. And this routine writes a byte to port A. Each bit in the byte corresponds to one of the 8 port pins. And finally, some initialization routines. The standard init SPI routine just sets the SPI pins to the correct idle state, and init chip sets the chip registers as required. If I needed to change the IO con register, I could do that here, but the power on value of 0 turns out to be okay for this demo, so there's no need to change it. I do need to change the IO direction register for port A, as both ports power up with all pins set as inputs. Each bit in the value defines the direction of each IO pin. 1 is input, 0 is output. So I need to set the lower 3 bits to 0, at least, so I can drive the LEDs. I'll just write a 0 byte to set all 8 pins as outputs. Okay, that's all the support functions I need, so I'll clear the screen and run them interactively. First, initialize the SPI signals. Then reset the chip hardware by taking the reset signal low for at least 1 millisecond. So that's reset and aux low. Then back to high for another millisecond. Reset aux high. Now entering these manually won't be a problem, but if you want to put these commands inside a routine, they will execute faster, so you may need to add suitable delays. Okay, now for the chip. Init chip. And finally, we're ready to control the LEDs. So if I say 1 write to port A, fingers crossed, bit 0 lights up. Let's try 2. That's the next bit. And 4. Try 5. How about 7? They should all light up. And 0. All off. I'll make up a quick test T to cycle through all values from 7 to 0. And just ignore the code if you're not familiar with fourth. I'm going to start a counter, write it to the port A, and test whether it's 0 or not. And loop back. Okay, T, watch the lights, T. Okay, let's repeat that forever. Do a test 2, call T, and just jump back and repeat. Test 2. Okay, that's all for now.